Okay, good day everyone. I hope you guys are having a good day. Today we're gonna be talking about face-centered cubic structures, FCC structures. My name is Ononogbu Chukwu, and I'll be doing this presentation for you today. So let's get into it. Our areas of discussion, we will be defining what FCC structures are with examples. We will be solving for the density of FCC structures, and we will be indexing FCC structures using Miller indices. Okay, so FCC structures. These are crystal structures that have a unit cell of cubic geometry with atoms located at each of the corners and centers of the cube faces. Okay, so first of all, crystal structures are structures that follow like a regular pattern. So, like for FCC structures, we have this cube, right? So it's going to be like replicated to form the whole entire structure. So now we're just trying to study like that unit cell, that singular pattern that's going to be followed through. So when you're looking at this single pattern, like the FCC pattern, you can see that there are six faces: one, two, three, four, five, and six. You can see the corner atoms like these small circles: one, two, three, four, five, six, seven, eight, nine, 10, 11, 12. And you can see how simple the structure is. So this structure is going to be repeated millions or billions of times to now form like the bigger structures, like to form bigger structures basically. So next slide. Okay, let me give you some examples of FCC structures. We have like our aluminium, copper, and gold. And this number here is our atomic radius. This is going to be very useful when you're trying to calculate maybe your density and some other important data. You can see the atomic radius number for your aluminium and the number for your copper, the number for your gold. Yeah, these are all FCC structures. So FCC structures, we know they have 8 corner atoms, 6 face atoms, and no interior atoms. The APF of an FCC structure is 0.74, and the coordination number of 12 is the coordination number for your FCC structures. So these are just a bit of like some data that you can use for calculations, or some data that you can use to identify which structure is FCC and which is not. So yeah, next slide. So now the good stuff, density calculation. So if you want to calculate your density for FCC structures, this is the formula we're going to use. Is your N times A, close the bracket, then you have your VC times NA. Your N in this case is your number of atoms, your A is your atomic weight, your VC is the volume of each unit cell, and your NA is your Avogadro's number, which is 6.022 times 10 raised to the power 23. So we have a good example of here. Calculate the theoretical density of the FCC copper, which has an atomic radius of 0.128 nm and the atomic weight of 63.55 gram per mole. So you just apply your formula, you plug and chug your numbers, and then you get the final answer of 8896.08 kg per meters cube. You also have to convert your units and all this stuff. Really quick, let me show you my 3D FCC structure. So yeah, these are just basically cubic structures. We all know what cubes look like, so this is like our crystalline structure that's going to be replicated. So let me try and move it around a bit. So you can see it from the top, you can see it from this side, you can see it from here, from the bottom. And yeah, it's really fun to think about, I guess, like how a structure, like how this crystalline structure can duplicate like millions and billions of times to form like the things we maybe use like almost every day, you could say. This is just like a general overview of what FCC structures are, but hopefully it gives you like an idea. Yeah, okay. So back to the presentation. Okay, so to quickly round it off, we'd have a look at Miller indices. Like, so this is a coordinate system that is used in crystallography to identify planes in the crystal. So coordinate system is like the one we've known like basically all of our lives with math. It's like when you say your x, y, and your z plane or something like that. So it's just kind of direct. It's just to give you direction. So like let's say like an architect wants to give you like you're gonna have to put like this metal sheet at so point. So he's gonna give you like a coordinate system to use like in the kind of design he's trying to build. So it's something like that. So let's say we're trying to identify like the specific cubic structure we're talking about in this huge material. So we give you like a coordinate system that you follow. In this case, I'm going to use the Miller indices coordinate system. So if you look at this, you can see that this is how you identify your directions. This is an example, like your A, B, and C. So your step one is to identify the intercept X, Y, and Z axis. It's very similar to your X, Y, and Z coordinate system. So you identify your X, your Y, and Z axis. You specify the intercepts in fractional coordinates, and then you take the reciprocal of the fractional intercepts. Like I said, this is just very like basic stuff, like just a summary of like the whole concept, but like it just makes you kind of relax to know that this is not different from anything you've done before. This is still like same coordinate systems we've used, so you just about adapting to this a bit. But that's basically what Miller indices is about. And yeah, this is just a very brief overview of FCC structures. Thank you.